Good morning, class. Today is November the 11th, and so this is the video for November the 12th. And this is our final process step that we're covering in the course on bonding. And it's mostly in the sections I put in the syllabus, but you'll see that it sort of nicely dovetails into the first device recipe that we'll talk about, which is work that I collaborated with a few years ago on producing what are called focal plane emitters, which involve bonding that's not gone over here, and we'll discuss that in a minute. And so, to a certain extent, the first recipe we discuss will augment this chapter. So, he states the sort of obvious at the beginning here, which is that bonding mates two wafers. Basically, if you have a situation where, for example, you have two types of semiconductor wafers and they are dissimilar, for example, one may be silicon, another one may be gallium arsenide, and you want to bond them together because you want the set of two wafers, the assembly, to have the capabilities of both. And so that's the usual reason why you do it. There are other reasons that are sort of touched upon here. Here I mainly want to convey to you the basic process of bonding. And this won't take long. But I'm just going to highlight a few things here. So before we go on, the author of this textbook is a little bit, he's focused on certain technologies, certain semiconductor technologies, including, as you've seen, micro-electromechanical system wafers. But when he says bonding mates two wafers, what you'll see, especially as we go into the first device recipe that I'll be covering next week, is that most of the time, actually, a lot of the time, you're not bonding two wafers, you're bonding two chips. And it's sort of an interesting question sometimes whether you are going to bond at the wafer level or bond at the chip level. And I guess I don't want to get up and start writing at the board, so I'll just say in words, and it's sort of, something that's perhaps a little bit obvious, that if you bond at the wafer level, we haven't talked about, making chips, but sort of obviously, wafers are composed of chips. You have, many chips on a wafer, and you saw up the wafer afterwards to separate them into their chips. And so if you bond at the wafer level, you may have to saw them through a two wafer bonded assembly, and that could lead to some difficulties. And so I think more of the time, actually, you are actually bonding chips because it's so difficult to perform sawing or dicing of wafers into chips when they're already in assembly. But anyway, moving along here, as said, you can bring together two wafers, you can bond them together because they may have different capabilities and so have different things to contribute to an overall device operation. Now, I just wanted to cover a few highlights here. And so this will be a short lecture. There's roughly two types of bonding. The first one is direct bonding. That's where there's no direct bonding is where there's nothing between the wafers, so to speak. You're taking one wafer and you're placing it in direct contact with another wafer, and you're doing something to cause them to bond together. And the second is bonding with intermediate layers. And there, you know, it's, I mean, I've never bonded semiconductor wafers together with an adhesive, although, you know, that gives you the idea of the possibility there. If you're simply making some sort of mechanical structure of two wafers, I mean, by all means, if you think using an epoxy can work, go ahead. But, you know, it gives you the idea that bonding occurs also with the use of essentially something you might call an adhesive, which may in fact be a low melting temperature metal. Now, if we talk about direct bonding, usually it's by what's called van der Waals forces, as stated here. And if you are going to attempt to bond together two different wafers directly, the thing you have to be aware of is that if they have even the slightest roughness, you know, here he says, you know, 0.3 nanometers. And 0.3 nanometers is basically on the order of an atomic roughness. That can translate into, because, you know, this is the roughness, that means in some places the wafer may actually be you know, as high as 3 nanometers from low point. And as he states here, van der Waals forces only work up to a half a nanometer. And so what you usually have to do is you have to apply heat. And the heat, depending on what type of material, if it's glasses or silicon wafers, causes the atoms to move a little bit so to overcome that surface roughness. So that's direct bonding, and I only assigned sections 1, 2, and 4 here, just to cover a few basic points. Now, however you're bonding, whether directly or with an intermediate material, usually it's at an elevated temperature. And depending upon how elevated it is, and how different the thermal expansion coefficients of the two wafers are, when you cool them down, it will result in stress. And I think that maybe I'll try and make up a homework problem on the types of stress that will occur when bonding two different materials, for example, gallium arsenide and silicon, to give you more of an idea about that. And you know, basically what happens is that, and when, you know, I don't want to get up and start working at the board to lose my focus right now, but when we talk in the first lecture next week about the flip chip bonding that I performed to make those devices several years ago, I'll discuss how the fact that the two wafers or chips in that instance have different thermal expansion coefficients, it means that one basically contracts more than the other, and so it acts to try to pull them apart. And so the first lesson is, however you bond, the bonding strength, whatever you use to bond the wafers together, must have a higher strength than the thermal stresses that occur due to CTE mismatch. Now, I have never done silicon glass bonding, but it is a special case that has a lot of applications. Perhaps you know, as later in the course, we'll look at some special applications of silicon glass bonding, but that's done by what's called anodic bonding. Let me quickly go over that. So it has its own section here, which is, you know, part of your material. Anodic bonding. So anodic bonding is, I believe, only performed for bonding silicon to glass. And It's shown here. So in anodic bonding, um, you apply pressure between silicon and glass. This is glass up here. And you also heat it, and you also apply a negative voltage to the glass with respect to the silicon. And what that does, all glass has sodium in it, and that acts to ionize the sodium and the oxygen of the silicon dioxide. And so it drives oxygen atoms toward the silicon glass interface here. And then at the silicon glass interface, this reaction occurs. Basically, the silicon reacts with the oxygen to produce SiO2 there. And so if you think about it, what you're doing is you're forming your interface bonding layer by forming silicon dioxide out of the silicon. So it's like the silicon dioxide starts to extend into the silicon and bonds extremely well to it. And like I said, I've never personally performed anodic bonding of silicon and glass, but I wanted to cover that as part of things I wanted you to know for the course. Now, as discussed, indirect bonding, well, he says there's three classes of materials that you can use, and he puts glues in parentheses here. And, you know, I mean, it is kind of like glue in the sense that that you're using like a low melting temperature metal or a glass to kind of melt into each other to form kind of, and it's kind of like a glue. That leads us to primarily metallic bonding, which is the section 17.4. And the one I know most about and can give you the most guidance on. Now basically, in metallic bonding, well, I mean, you can imagine if you're bonding two wafers together, that if you put down a metal on both surfaces and you press them together, and so you apply pressure or compression to the two wafers, pushing them together, that and at the same time you apply heat, that the metal you've put down can sort of melt into each other and form what is essentially a weld. Now, what he says here is true. Gold is frequently used because as a noble metal, it does not oxidize. And so gold bonding is something that you frequently see. Now, I highlighted wire bonding here, and I'm not sure. What I'm going to do is that if we have time at the end of the course, we may get into what's called semiconductor packaging, where you know, I might teach you the techniques by which you put or integrate semiconductor devices into a package that you can then install on like a circuit board or something like that. And wire bonding is, of course, still very important. It's the primary technique by which contacts are made to a chip, and so maybe we'll come back to cover that. But he's correct that in wire bonding, frequently the wire that is used is gold, and it is bonded to, well, usually it's actually aluminum pads on the integrated circuit. And I could tell you a lot about gold aluminum bonding that you don't want to know, but we'll maybe cover that too. Now, what eutectic basically refers to an alloy, but basically I've never used gold silicon, but I wanted to highlight here gold tin as basically a low temperature alloy of gold. that is frequently used as a bonding material. Now, what's pretty interesting about this textbook, and I guess, you know, to, to him bonding was important enough to make a chapter about it, and it is an important semiconductor process concept. It's, of course, a lot different than things like lithography or etching, or things that are used, you know, to make, you know, submicron transistors and things like that. But bonding is frequently used, and he doesn't mention really what is the most important bonding metal, which is indium. And so you know, maybe I'll stand up and turn the projector off and go through a little bit. Well, I can leave the projector on, maybe, turn the lights on. So I just wanted to end today's lecture by discussing with you that, in fact, the most important bonding metal is indium. Oh, there we go. Maybe I can do this one too. And it kind of surprised me that he didn't discuss it at all in the textbook. It's important for two reasons. Because one, there's a very low melting point. Now, that doesn't really, that's kind of important, but not for the reason you think. We're going to discuss next week flip chip bonding. And in flip chip bonding, you're taking two chips, and you're not just, you know, using an entire layer of metal here. You're using what are called flip chip bumps. So in a machine that I'll talk about, you bring these chips together, and so this indium, these indium bumps are pushed together. And what happens is that when you take two bumps of indium and you push them together, in fact, you usually do that at room temperature or very low temperature. And what happens is that it's actually somewhat not completely understood how an indium bump pushed against another indium bump forms a weld. You know, sort of the example I've used is that it's kind of like pushing two marshmallows fit together, although I've never actually tried pushing two marshmallows together. But you don't melt the indium. You push them together, and because the melting temperature is so low, the indium atoms in one of the bumps kind of like pushes into the indium atoms of the other bump, and you form an extremely good weld. And so if you ever have to, you know, perform any flip chip bonding in particular. Now the other reason is that indium has high thermal conductivity. Okay, you can see that. Because, I mean, when you bring these chips together, all right, usually only one chip can be mounted in the package where the heat can go. And so the heat of one chip has to flow through that bond. And so N-beam is particularly useful because, especially of low temperature melting metals, it has a very high thermal conductivity, and so can convey that heat. All right, and that's all I was going to do for today. So this finishes up all the process descriptions we were going to cover in the course. Again, there might be, some, we haven't talked about, sawing up wafers and things like that. So there's more to know at what's called the back end of the processing. Once you have the chips processed, how you package them and things like that. And some people think bonding is part of the packaging, so to speak, and it is in a lot of cases. Here he's more discussing in terms of fabricating sort of a chip assembly, but maybe we'll have time later in the course to talk about some packaging. Okay.